Okay, so it's time for our fourth lecture. Last time we saw just a basic introduction to proving things, and now we're going to get into more detail with some more interesting forms of induction and recursion. So probably you've had a lot of proofs fail already. The thing is, just like with programming, you have to do everything perfectly. So even if it is more or less correct what you're doing, somehow you can't prove it. Very often this is because the formula you're trying to prove is not what we call inductive. So it is not strong enough in the induction step to push through to the next stage of the induction. It may be you've got the wrong induction rule. This actually seems to happen a lot in the exercises. So typically you might have a thing about the natural numbers. There's the obvious induction rule for the natural numbers. Usually you can prove your thing using that induction rule, but somehow you end up doing 5 times as much work as the person who used a different induction rule. Or the cruel hypothesis, the cruel reason, which is you're just not quite clever enough, but then that applies to us all the time. Well, here's an example. Now, what this example is, so you may have seen, for example, in my own ML course, if you've seen it, or elsewhere, the idea of the length of a list, which has an obvious recursive definition. Now, in Isabelle, the length of a list is called size. So size is, in fact, a polymorphic function, and size works for trees and all kinds of things. But for a list, size has the obvious recursive definition. The size of an empty list is 0 and so forth. Now, if we are worried about efficiency, you'll all have learned about tail recursion or terminal recursion in some functional programming course, and you know that you can use an additional argument, a so-called accumulator, to get a more efficient function. So that function at the top, called itlen, is this iterative way of getting the length of a list, whereby you, as you can see, you got n as your extra argument, and when you're at the end of the list, so nil, you just return n. And if you have a non-empty list, you add 1 to n and do the recursion. And the obvious hypothesis is that itlen is the same function as the normal length of a list. Now, we see that n is part of the problem statement, so itlen involves n, so we at least have the brains to say the relationship we want has to mention n, so itlen of the list and n is then equal to the size of the list plus n. But if you think you've solved the problem, you're wrong, because you see what happens here. So we do we set up our induction, we do the induction, we apply the induction tactic, we apply auto, and something is left over. So what is left over? Sorry, there we are. I said all this. Sorry, I should use my own builds. What is left over? Well, we have an induction hypothesis talking about itlen of xs, which is our induction parameter, and the number n. But our induction formula that we're trying to prove involves suc n. Well, that is unpleasant. Now, if you think about it for a moment, okay, you know that with induction, you get an induction hypothesis for a smaller value, right? So you might think we're stuck here, that's just the way it goes. But no, you see, the thing we're doing induction on is the list. So it's the list that needs to be the smaller value. There's no reason why n should, so we shouldn't have a mismatch about n at all. But how exactly do we put this right? It's not so clear. Well, we can, if we want to leave this in our file, we can put an oops there. That tells Isabelle to just give up, but it allows you to leave it there without it interfering with what comes after. So let's do it properly. Now you see that universal quantifier there. So from a strictly logical point of view, this formula expresses the relationship we want. So whereas before we just had n, now we're saying this is a property that we want to hold for all n. And now you see the list, xs, is a free variable, same as before, but n is no longer a free variable. So what we are establishing, remember in any induction you do your base case, and then as you go through the induction step you go up through the cases and so on, and what we are building up is that quantified formula for all n, but at first only for the empty list, then with one element list, and so on. So this formula is inductive in the sense that it is strong enough to push you up to the next step of the induction. And now, what you see there, you see your induction hypothesis of the form for all n. Okay, so the induction hypothesis is still restricted to the shorter list, namely xs, but now it holds for all n. So now we won't have the problem we had before. So this time the proof will work. A complaint you might make is it's a little ugly, and I don't like to see this universal quantifier there. So you can do this. This is just a cosmetic thing to make it look nicer. So this keyword arbitrary basically is telling Isabel to pretend there was a quantifier there. In fact, it will insert a quantifier itself. Now, in fact, it uses, I will get to the thing I'm about to say will be explained in a later lecture. That funny symbol that introduces the parameters of a subgoal is kind of a meta-level universal quantifier. So what we are doing here is we are putting in the inductional hypothesis is quantified for all n, only this time the quantifier is the built-in one, which you see it looks different, but it has effectively the same meaning, and then we can prove this. Okay, now quick question. If this works better, why don't we always make all the variables arbitrary except the one we're doing the induction on? Well, that is the most general way to work. But the problem is putting in quantifiers when you don't need to is making your life more difficult. So, and sometimes I literally do this. I might make a bunch of things arbitrary, and when I can see that it's not necessary, I'll then remove variables from that list to have the list as short as possible. So the point is here, the arbitrary for n is needed. And I guess you can tell in advance it's needed if you are aware of these things, simply because the value of n changes in the recursive calls. Whereas if you have a recursive function and you sometimes have arguments that don't change in the recursive calls, and typically they don't need to be listed as arbitrary. And then you have fewer quantifiers to worry about. Okay, moving on to a different thing. So I hope you've all seen Ackermann's function before. Ackermann's function is really cool. Actually, the function invented by Ackermann doesn't look like that. But it was simplified by others. But nevertheless, Ackermann's function, you see, involves two arguments. The funny thing is, and if you've played with Ackermann's function, it's just a kind of nested recursion. In fact, yeah, let me go back. That isn't the point I wanted to make, actually. So we're doing recursion on both arguments. So first, I guess the second argument gets smaller, and then the first argument gets smaller. And to make it even worse, if you look inside the last line of the Ackermann function there, you have a nested recursion. So ACK is applied to a recursive call on itself. So there's something awful about this, and this is why, as I guess you all know, Ackermann's function grows more quickly than any primitive recursive function, which means, in effect, Ackermann's function can easily create really quite unimaginable numbers. So if you know any physicists, when a physicist talks about a really big number, they might say something like 10 to the 40, because or something like the number of, I don't know, neutrinos in the universe might be more or less a number of that sort, which to a mathematician is still a minuscule number, because you can make numbers much bigger than that just by using Ackermann's function with, I think Ackermann's of 4 and 3 is already way bigger than 10 to the 40. Anyway, we have a 2-argument function, and when we prove things by induction, we might want to use induction on 2 variables. But what do I mean here? Well, we have got a special induction rule. So every time you use fun, and this is like the built-in function definition package, which you will use whenever you introduce recursive functions, if you put in a function with some slightly odd recursion like that, and in fact, even if you have an absolutely vanilla recursion, it will give you an induction rule just for that function, and the idea of that induction rule is to do an induction on exactly the same termination argument as the function had for itself. This will usually make your proof simpler. Now, if you look at the function definition closely, you might guess this is in fact 2 nested primitive recursions. In fact, the question of why is it then not primitive recursive if it's 2 nested primitive recursions? And the reason is that the kind of, I guess the inner one is making a function value which is not allowed in the primitive recursive function theory. And by the way, if you haven't had any primitive recursive function theory, you can just forget that. So you could prove things about Ackermann's function using 2 instances of normal mathematical induction. Nevertheless, it's quite a bit slicker doing it this way. So there is a particular theorem. That's a very simple theorem, right? J is less than Ackermann's of I and J. And this, by the way, comes from a proof that Ackermann's function grows more rapidly than all primitive recursive functions. This proof is, in fact, distributed with Isabelle, so if any of you are interested in that, it's there. And this proof is super easy. So, by the way, what I'm showing you there down below is the sub-goals you get after Ackermann's, after just applying the induction rule. So I start with J less than Ij, I apply induction, and that's what I get. And the point is, if you look at the induction hypotheses, you have an induction hypothesis for exactly the recursive calls that the function is going to make. And that's exactly what you want. So if you're trying to prove that your property is preserved by the recursive calls, you need induction hypotheses that match those recursive calls. So this will be a trivial proof. Yeah, I don't see the rest of the proof here, but I think that it is nothing difficult. Okay, so just to recapitulate here, when we talk about primitive recursion in Isabelle, and I think in the ITP world, we are talking about recursion in one variable that is following the data type declaration in an obvious way. This is pretty close to, but not identical, I guess, but pretty close to what they call primitive recursion in a computation theory course you may have had. But we're not only talking about natural numbers here, it could be some binary tree type. Anything that does the obvious structural recursion, we might call primitive recursion instead. Isabelle has a very nice thing called fun. I should mention, in different theorem provers, recursion will be given to you in different ways. So in Isabelle, it has a quite powerful logic called higher order logic, from which other forms of recursion are derivable. I believe this is not the case in Koch, which is, of course, the other leading proof assistant, where they build in certain recursion principles into the kernel itself. So they have a rather different approach there. And likewise, thinking of, there are many higher order logic theorem provers like Hall and Hall-Light and so on. They also have recursion derived from higher order logic itself with the help of, I have to say, a lot of code. So when you use fun, and by the way, fun has many, many variations. It gives you the induction rule I mentioned, and it is a very powerful thing, so it can handle things like nested recursion, pattern matching, very sophisticated termination arguments can also be done using fun. If you're interested, now if you go into your Isabel session, go to the documentation panel and look under, I can't remember, is it called the function package or the recursive function package, and you'll find all you want to know about this. Okay, so a bit more about these induction rules. Okay, I said this. We want to follow the function's recursive calls, and for Ackermann's function, this is what it looks like. So we already saw a proof with Ackermann's function where I showed you what a particular thing expanded into. What we have in general, so what I've done here is basically write the induction rule for Ackermann's function in kind of English with bullet points rather than trying to fit a logical rule on the slide. So to prove something of the form Pxy, where P is an arbitrary proposition, you have P0n, which you have to show for all n, and that of course is all the base cases of Ackermann's. Now, if you prove everything of the form P of suc m and 0, that will be another case, and here your induction hypothesis of Pm1 is of course following the recursion, and likewise for P with two successor arguments. And again, you can check that the inductive hypotheses you get match Ackermann's. Now, in general, for an induction rule to be sound, for it to make sense, basically it needs a termination argument which is exactly analogous to the termination function for a function definition. Now, I think I should, when I say usually it does what you want, for example, in the case of Ackermann's, in the example I told you about primitive recursion, that theory derives a bunch of things using Ackermann's function induction. Then at a certain point, some of the lemmas are using the previously proved lemmas, maybe with a different induction. So at some point, the reason the lemma holds is not by induction on the computation of Ackermann's anymore, but by some other thing, something's being iterated perhaps. So you need to look at the thing you're trying to prove and decide whether the property that you want is following from the computation of Ackermann's function, or rather it's being proved by other known properties of Ackermann's function. The thing is, when you're sitting with a powerful computer in front of you and powerful software, it's really tempting to play it like a computer game, mindless, and, a glass of wine, enjoy yourself. And you can go, if you have the flow with you, so to speak, you can go quite far. But you have to know when, at some point, you'll find yourself trying everything in a random way. And then you say, you get up, take a walk, and then think about the problem. Here we go. Well, you'll have to do a survey at the end of this course. Okay. Now, this is a nice example because it's very computational. I guess you're all from a computer science background. But although it's a simple function, it's not primitive recursive. You see, of course, this is a thing that merges two sorted lists. I hope that's obvious. So the x sharp sign xs, that is the cons symbol in ML. So that's two non-empty lists with head x and tail xs and so on. And we're merging them in the obvious way. If x is less than or equal to y, then you take out x and you continue merging. Otherwise, otherwise y is the smaller one, and we put it in front, and then we continue merging, and so on. So we have two recursive calls, and it's not primitive recursive in either argument, because in fact we're taking a double cons case as the thing we do recursion on. Then we have the two nil cases are treated separately. Now, what I've got there, so the proof below the definition of merge, is a very simple special case of the correctness of sorting. Now, if I were to prove a sorting function correct, of course, what does it mean for sorting to be correct? Well, the output of the sort has to be sorted, and the elements in the output have to be the same as the elements in the input. Now, it turns out that either of those conditions by itself is trivial to satisfy and is not very useful. So you need both. And in fact, strictly speaking, it's not enough for the elements in the output to be the same as the elements in the input, but even any repetitions. So if I've got 27 copies of 2, they should be preserved in the output as well. No, I'm not doing that here, because to count the multiplicities of elements, you need multisets, which I don't want to get into. So you see what I'm showing here is merely about sets, so I'm actually ignoring the multiplicities here. You can forgive that. All I'm proving is that if you merge two lists xx and ys, regard it as a set, then that set will be equal to the set of all the elements in the first list unioned with the set of elements in the other list. As I said before, we will use the special induction rule for merge. If you didn't, so let's say you actually said, I just don't like special induction rules, I'm going to do it some other way, it would be a pain. I think you would have to do induction on something like the sum of the lengths of the two lists. And a lot of mathematicians will do that. See, if you look at a typical mathematical text, they don't tend to talk about special induction rules because they don't tend to take a kind of syntactic view of induction at all. So they would say that we should look at the sum of the lengths of lists, and that would be fine for them. But if you do talk about the sum of the lengths, then you're kind of involving arithmetic in a way that is not really relevant. So there we are, we set up our goal and we did induction, and those are the things we've got below. So you see in particular that we have two induction hypotheses, one for the x less than or equal to y case and the other for the negation. So for x less than or equal to y, we have a case which corresponds to the first recursive call and the other one for the second recursive call. So this again is a trivial proof. Now what I'm doing here, maybe I shouldn't this time because we saw a slow kind of step-by-step rewriting before, but maybe it's worth going through this one more time. So you see on the we've got at the top of the slide the identity we're trying to prove, and now we can go through it by rewriting. And the first step will be we take the definition of merge and we expand it out into its right-hand side, which will be the line below with an if-then-else in it. Now that if-then-else, I told you last time about case splitting, right? So an if-then-else will be automatically split by the simplifier. So that will turn into the line below, where we have the conjunction of the x less than or equal to y and so on. So our original identity has been turned into two identities to be proved. And now what happens here? Now we have our two induction hypotheses. So the first highlighted bit there of the new highlighted bits, the first one is under the assumption x less than or equal to y. And we have an induction hypothesis for that case. Likewise, the other one is for the negation, and we can use the induction hypothesis for that case as well. And that will rewrite in a couple of steps. I should go back, but I can't go back to the start, so I won't do that. It will rewrite to the thing which I just got there, where I just put in the new highlighting. So you see the X on the first one, the X comes out. With the second one, the Y has come out. Oh, sorry, I goofed. So everything I said about induction hypotheses applies to this case, not to the one before. So sorry about that. What is happening on the line before is simply the definition of set. So that's a set of a list that has an element added to it. But now we are indeed in the case of the recursive calls, and we are now at this point using the induction hypotheses. And that then, so the result of applying the induction hypotheses will put in more unions there. Oh, sorry about that. That is the last one. I'm having a bad day. Anyway, so at the very bottom, what had happened there, the last thing that is coming out is the application of the induction hypotheses. And it's not immediately obvious. I guess you need to think a bit more before you can see that it's equal to the right-hand side, but I thought I was rewriting enough for you. In particular, what I wanted to show you is how the if-then-else here turns into the implications on the next two lines there that allow the induction hypotheses to be used. And that is also how the function package gives you not a single induction hypothesis with an if-then-else in it, but rather the two induction hypotheses. Okay, let's go through this, and finally, our well-earned second Dilbert. Is that you? Yeah, well, oh dear. Okay. Now, I have one more example, and to get to that, I need to explain the thing. Actually, one of you asked about case before. So let's look at this. If you've used something like ML or OCaml or Haskell, you know that you've got recursive data types, recursive structures, and that you need the ability to do case analysis on them in an expression. So we have something like that, only it's very crude. We don't, because everything is kind of template driven, we don't have the sophistication of a real compiler. But anyway, you can do case analyses on structured data types as long as you go through all the cases in the right order, in the same order as you declared them, and don't try anything at all clever. So every data type has a kind of internal case operator, which is then mapped onto the case syntax in a very literal way. That said, no reordering or nested patterns or anything sophisticated. Now, in general, so I've told you before that if automatically case splits into a conjunction. This does not happen automatically for the other case operators, but there is a bit of magic you can do that will cause it to happen, which I will show you on the next slide. So you can optionally specify case splitting, and usually it's something you want to do. Similarly, even with if, as I told you before, an if in the assumptions does not split unless you ask for it. So here we have the example of list, and I have a particular thing. This is actually the rest of the proof. I told you I was going to give you a correctness proof for merge sort, and this will be the rest of the proof of the rest of the correctness proof. If I want to show you that merge gives you an ordered result, we need to define the notion of ordered, or sorted, if you prefer. So here's one definition. You see the empty list is sorted, every one element list is sorted, and for longer lists, we want the first two elements to be in their order, and furthermore, if you take away X, what you've got left also needs to be ordered. There's another way of writing that. And I guess this way of writing it using case, well, it allows me to show off case, but it also, I think, is a bit better for proving things, because then when I automatically split the case, I will get some shorter proofs. So this is the same as the previous definition, except now when I have a non-empty list, I look at the tail, and if the tail is empty, we're done. If the tail is not empty, we have basically what we had in the previous version of this. Now, when you look at this, as I said, with case, the things have to be in the correct order. So first nil and then cons, because that's the order of the original data type. So now, when we try and do our proof, as I said, to complete our proof of merge sort, we need to show that the merge operation preserves both the elements and their order. So here we're trying to show, and this is a strong property, in fact, as you see, you probably can't see that clearly, there's an equal sign there at the top, right? So I'm proving something stronger than I need. Not only am I proving that two ordered lists end up ordered after you merge them, but I'm also proving the converse. Clearly that's a stronger property, and it might also make the proof easier, because if you have a stronger assertion, you will have a stronger induction hypothesis, and instead of having a conditional claim, you will have simply an equality. So there we are, we do our induction, and then you say, oh, and I try not to use bad language, so I didn't use any bad language, but you say, oh bother, that looks bad. And this is why automatic case splitting was invented in the first place, because there are something like half a dozen separate cases there on Y. So as I told you last time, if you find yourself faced with an awful mess, look carefully and see if there's anything that you could be getting rid of automatically. So you say, yes, there's a lot of cases, and we need to invoke a case split. And that is how you do it. So what I'm going to do now, this thing called split can be used with auto and simp, and you have to give it a splitting rule. So typically for the type list, you have a rule split, which does the things in the goal, and for splitting in the assumptions, it's split underscore ASM for assumption. So if we now apply auto with split, it's done. It was automatic. But there's a bit of a cheat here, so if you look very carefully, you'll see that something is missing from the end of the proof. So what needs to be there is that. So I need to delete. So you see, in the first step, I simplify everything, and in the second step, I do all the splits, but deleting one of the rewrite rules for ordered. Now, what's happening in detail perhaps maybe doesn't concern you very much, but the problem is we did get looping, and it happened because basically what happened here was wherever we had case over a list, we replaced it by a conjunction where we have in the first part empty list and in the second part non-empty list. And in the non-empty list case, if you don't have a simp del that I showed you in the previous slide, it will split open the definition of ordered again, give you another case, and then this thing will split it, and it will go on forever. Have any of you had the simplifier loop on you yet? Oh, you've all been lucky. It doesn't happen actually that often. It is awfully aggravating when it does. Yeah, so this case split will give you a case for each constructor. And the looping, as I mentioned, when the looping happens, it turns purple, as we will see in a moment. So I just want to recap the material we talked about today. That recursion takes many forms. And I have to repeat this because it bugs me when an exercise has a solution of 15 lines and someone gives me 75 lines because they adopted the wrong approach. And you might say it's actually quite easy for a proof to get longer and longer. And I suppose if it's going well and you can see your route to the end, you might not want to kind of give up and change course. So I can see why people have done that. I still feel a little bad, marking them when I know there's quite an easy proof if only you use the correct induction rule. But certainly, when you've just defined a function, or in fact later on we'll also have inductively defined predicates, you'll get an induction rule. Do think about using it. We have our nice case operator, but we have a risk of looping. I know there are some notes in the slides that are not on the slides themselves, and I can't remember whether it has more about how to invoke splitting in there because it's probably not very clear to you. Luckily, you probably won't need splitting very much. Now, that purple, if you can see there, the purple line, wait, is it? It's not actually looping. The reason that is purple is you see the line above, which is in a lighter purple where it says using simp trace. So that line is telling Isabel to put the tracing on for simplifier. Now you see, in fact, whenever you have using with those double brackets there, that allows you to set flags to be true or false to control a whole bunch of things. And although the line below is purple, it's not purple because it's in a loop. It's not in a loop because the simp del is there. But it is working incredibly hard because simp trace causes it to dump out thousands of lines of text. And because it's working hard, that's why it's purple. When it's in a loop, it will be in the same color. So if you see anything turn purple on you, it is at the very least working very hard. And then you might want to check in the output panel to see if it's spewing out tons of junk of some sort, in which case you should probably delete that line. There is, of course, no way of killing a thing in JEdit. The way Isabel works, if the line is there, it's executed, and the only way to kill it is to delete it or to put an oops in front of it. So what you see down below there is a trace. It's not. Is it that easy to read? I don't know. You can see that ordered of empty lists is being replaced by true in a couple of times. Something ANDed with true is being simplified. So I guess it is possible to look at the individual rewrites. It's not necessarily that easy for you to figure out why your thing is looping in the first place. So typically, it helps if you can guess where the problem might be, so you can search, because that's just a normal editor window, and you could search in there for a thing that you're suspicious of and see if there are like 100 occurrences of the same thing, then it's probably the thing that's looping. Okay, so that's a little thing to note, and that is the end of the lecture. Now I think, let me just